It's a great pleasure now to introduce Dave Beauchamp. Dave is a fisheries biologist with a worldwide reputation. He got his degrees from the University of Washington. He's currently a professor there, along with an appointment through the USGS. Oh, Charles, you shouldn't have. Thank you. He's worked on Lake Tahoe for a long time. After completing his PhD, he actually did a postdoc for several years studying the fishes of Lake Tahoe. So you're all here to listen to Dave, not to me. So unless Charles wants to say something else.
Of course. A brief announcement. I think all of you knew that Heather got the special award from the Tahoe Regional Planning Agency. I only found out about it reading the newspaper today. Good to see you.
And when Dave was doing his postdoc here, Charles was his advisor. So on that note, Dave.
All right.
That musical note.
Thanks, Jeff. Well, I was trying to figure out, it's been probably 15 to 20 years since I was working up here, so it's a real pleasure to get back involved again. And what I'm going to try and do is piece together some of the information that we've acquired in the past. And we just did get underway about 2 months ago, so I will be showing you a snippet of what we're doing currently and try and synthesize that in a way that we can start to address a few questions related to this open water food web in Lake Tahoe. We're focusing on that because historically the Lahontan cutthroat trout were pelagic, and also during my previous stints here in Lake Tahoe and actually most of the other studies, we've been undergunned in terms of our ability to sample the open water environment for pelagic fish. And so I'm real excited to be able to take that on with more capability now, and I'll show you what we mean as we go along. I'd also like to just take a minute to acknowledge some of the collaborators here. I've got 2 graduate students that are working on a project. Allison McCoy is going to do her master's degree on this. Adam Hansen is doing this just on a small level. He's providing some hydroacoustic expertise to help out Allison. And then U.S. Fish and Wildlife Service is providing funding and the vessel support that's getting us out there onto the water. So with that, let's keep going. You're probably all aware of this since I stole this off the website here. What I primarily want to show you, though, is that we've had a variety of fish that have been introduced throughout time. Before 1940, the Lahontan cutthroat trout were extirpated from this basin, and it was largely thought to be a cause from overharvest, degraded streams. We don't really know what role, if any, the food web played at that point, and so that's one of the mysteries that kind of affect how we view the project currently. And then very significantly, Mysis relicta was introduced and then became established in the lake later on and had a very extreme effect, not the least of which was the extirpation of Daphne, a major zooplankton resource, and a whole cascade of events that occurred as a result of this introduction. So what I want to do is just briefly go through how we're trying to approach this question here. And so what we're trying to do is examine the current lake conditions and ask the question about how food web interactions in relation to how it was historically and currently are projected to affect these relationships with Lahontan cutthroat trout and either pose some obstacles or facilitate growth and survival of these fish at different life stages. So we want to consider a series of filters that are both in terms of the physical processes that are underway as well as the biological ones. And we'll use these as hypotheses to try and examine what types of processes are actually influential in affecting the population dynamics of not just Lahontan cutthroat, but the existing populations here. And we can address these hypotheses both by synthesizing some of the existing information we have and then plugging holes based on directed sampling that we're currently underway trying to do right now. So first, let's try and define the niche in terms of some of the physical habitat. In large lakes, oftentimes temperature really drives much of what's going on with the upper trophic level animals, primarily because these are all mobile. Fish can move around. They have their own temperature tolerances, and so they can move to areas that can either optimize their growth or minimize some stress. And so it's often a very strong structuring feature in large lake habitats. And then we'll also consider some of the ecological interactions that are underway. Things like what food is available to them. Are there competitors that are also potentially reducing that same food supply? And are there predators that could pose significant mortality on these fish directly, or actually take them out of their normal ball game and alter their behavior such that they have either less access to food or it alters their growth environment in some other way? So how do all these factors interact? We often see that these ecological factors are mediated by the environment in which you're in. So you could have the same collection of species in a different lake, and because either the bathymetry of the lake or the environmental conditions that are there, you'll see some radically different responses. And so it's a little bit risky to play the game of using anecdotes and applying them from one system to another. Because there are mechanisms that are underway. What we're trying to do is understand these mechanisms, because what worked in one system doesn't necessarily work in others. Okay, so we'll go back and talk a little bit about the environmental niche. And again, this is going to be both a function of the thermal regime within the lake, but also how the fish respond to it. So we're going to have to delve into bioenergetics briefly to tell you a bit about how fish respond in terms of their growth regime across a range of temperatures. What temperatures optimize growth, which temperatures actually suppress or even put them into a negative growth environment, so that they may be able to tolerate that for a short period, but over the long run they're going to starve or they'll be debilitated and some other cause of mortality will remove them from the population. Okay, so we'll look at the thermal regime in the lake, and that'll be in terms of looking at the vertical temperature profiles on a monthly basis. And then we're going to overlay that with the bathymetry of the lake so that we know that bottom landscape, how that intersects with the thermal regime, to give us a better sense for where this open water pelagic habitat ends and where that benthic habitat starts up in relation to the thermal regime. And then we'll come back and overlay some of the ecological interactions that may play out there. And so there are going to be a couple of these slides that have some graphs here, so just bear with me a little bit. On the x-axis, what we have is temperature, and this spans the range of the temperatures that you might find salmonids in general. Every fish species, in fact invertebrates as well, will have a characteristic set of functions that define how they respond to temperature. This happens to be the functions that would work for kokanee or sockeye salmon, their anadromous equivalent there. And what I want to show you is that if there was unlimited food available, the fish would still be limited in terms of temperature. You see this dome-shaped curve here. That would be the maximum amount of food that they could consume in a particular day based on the temperature they're exposed to. Now, in terms of their energy budget, they lose energy from waste, and so waste is typically almost a fixed fraction of what they eat. And so if we drop down to this red curve here, this would be the amount of energy that's now left for either growth or all the metabolic types of costs that these fish have. And then this green curve on the bottom is the metabolic costs. So instead of seeing this dome-shaped relationship, what we see is metabolism tends to go up exponentially as temperature increases. And so what we have left then is the distance between these two curves is the amount of growth that's available to those fish at a given temperature if they were feeding at their maximum rate. But in nature, it's uncommon for that to happen. Usually food is limited to some degree. And so if their ration size goes down to here, then waste also has to be taken off. And so you've got less of that energy available for growth, and so naturally they'll grow less. And what we're going to do now is remove all of these curves, and instead what we're going to do is look at just this this space here. So how much growth could they enjoy given the temperature regime that they have? And we're going to play around with different feeding rates so that we can look at, say, a very productive system. They could feed closer to this 100% of their maximum consumption. At more moderate feeding rates, they may be at 50%, and then down at lower rates would be 25 or less. And so we can look at how these growth relationships change as a result. And so here's that original. This is the growth curve that would have resulted from that first set of curves I showed you in that last slide. And then if we reduce their ration to 50% of the maximum, their growth naturally goes down. But the other thing that happens is that the temperature at which they grow the best also shifts to a cooler temperature. Okay, and then that becomes even more extreme if you reduce the feeding rate even further. What's probably more important, though, is that their thermal tolerance in terms of them not losing weight also shifts to cooler temperatures here. So there's not much of a change between feeding at their 100% rate or 50% rate. As these lines intersect the x-axis here, this is where they would start losing weight if they exceeded those temperature regimes. But if you go from this 50% line to the 20% line, now, instead of being able to tolerate up to about 23 degrees centigrade, now we're backing off to about 17 degrees or so. Okay, so this starts becoming a real prohibitive barrier for fish to cross, at least on any sort of a chronic level, because there are real costs involved in them being able to grow. Growing, as you'll see, is related to their survival and, of course, reproduction. The bigger these fish are, the more eggs the females can produce, and so you can have a lot more reproduction, more growth, more survival. Everything's better if you're bigger. So the sorts of things that are going to affect the growth environment are really important in terms of defining the quality of the niches that may be available to these fish. The other thing that happens is that not all sizes are created equal. And so what happens, the youngsters, the rates run a lot higher. I think we're used to that, right? The toddlers are just running around like crazy. They're also eating a huge amount relative to what their body size is. And as we get older, our metabolism slows down, and we're eating, well, the fish are actually a little more extreme in this regard. But what happens is that the maximum amount that they can eat, given their body size, and this is reflected in terms of, say, a percentage of their body weight or a proportion of their body weight. So a fish that's only at 1 gram, so that'd be about this size here, is feeding at, it's capable of eating upwards of 35% of its own body weight in a day. Whereas you go up to a kilogram size fish, now they're only able to eat somewhere around 2-3% of their own body weight in a day. The problem is that this feeding curve is a lot steeper than the waste and metabolic cost curve, and so as these fish get bigger, the amount of energy that's available from what they eat declines. And so if a small fish is able to eat at their maximum rate, they have roughly 50% of that energy is still available for growth. They can convert that right into growth, whereas these larger adults, this is about a 2.5-pound fish here, only about 33% of that energy is actually going to be available for conversion into growth. And so you've got temperature things that can affect the growth environment, but the growth environment, that same location in the water column, its benefit can change based on the size of the fish that occupy that as well. So those are important concepts to keep in mind when we talk about the niche. And so we can pile all this stuff together into these energetics models to do a lot of the bookkeeping for us, and they will have, for a given species, they'll have these curves involved in them. They're an energy balance equation, so it allows us to say if the amount that they eat has to equal the metabolic losses, the waste losses, and then whatever is left over is available for growth there. And so we can either use these models to estimate the amount of consumption that was needed in order to satisfy this growth rate, or we can flip it around and say, how much growth would you get if we specified a certain amount of consumption there? And what makes it easy for us then is we can now focus on just a few types of data that we collect in the field in order to feed the model and use those things as inputs. The other important feature is these models will operate at a daily time step, and so we can start capturing dynamics of things that are happening certainly on a weekly or monthly or seasonal basis, and most certainly on an annual basis there. So if there's some important events that happen over a fairly short time frame, if we're sampling to capture that, we can actually integrate that directly into this sort of a modeling framework and try and sort out what those trajectories might be. So in the field, what we're trying to do is figure out what temperatures these fish are exposed to. So remember, they can move around through the water column and potentially choose their temperature. So what we need to do is overlay that vertical temperature profile from the lake with their position in the water column. And if they're moving up and down in the water column, we have to do a time budget of how much time they're spending in cooler water and warmer water, and then spread that, do that across the calendar so we can document what their thermal regime would be over time. We also need to know how their diet changes through time. So they may be eating some certain sorts of prey in the spring, and that may transition to other sorts of food items later in the year. And so you want to capture that as well as both their feeding rate changes and their diet changes. And then very importantly, we need to know what their growth rate is over that time, because again, we're trying to balance growth to solve for consumption or go the other way around. So we need weight at one point of their life and weight at another point in their life in order to do this balancing act here. And then not all foods are created equal, and the condition of the fish aren't always equal either. So we need to know what the energy content of these food items are. So if I were to give you a pound of lettuce and have you eat that versus a pound of hamburgers, you're going to get a lot more energy out of the hamburgers there than you would the lettuce. And so we need to do that sort of a calculation. And also, as these fish change both in size and condition, their own energy content can change. And so doing the math to figure out how much energy actually is needed to grow that fish is going to be important to consider when we do this type of an analysis. So we can use these models to do a bunch of different types of scenarios, but the key thing to note here is that when we're in the field, what we're trying to do is grab the data to feed this part of the model. Okay? We can also use field-generated information to get these energy density values that we would grind up these samples and put them in a bomb calorimeter, and it would tell us how much energy there is per unit mass of those tissues. But we can also use literature values if we don't do that measurement directly as a default. Okay? So now that we've got all this information in hand, what we can do is start talking specifically about LaHunt and cutthroat trout in Lake Tahoe. Okay, so we've got 3 different sizes of fish. Here's that temperature regime again, and what I've plotted are growth curves for these guys, assuming they're feeding at a moderate rate of about 50% of their maximum. By and large, if we look across the globe, fish that are feeding on invertebrates and especially on zooplankton, we would expect them to feed at somewhere between 50 to 80, occasionally up to 100% of their maximum body weight or their maximum consumption through the year, especially the young guys. If they're feeding more on fish, then we would expect the long-term average to be more around 40% or so. So we're just using these as ballpark figures, but they're grounded in a fair amount of empirical support based on experience in a number of other systems, both large lakes locally and around the world. So what we've done is plotted these curves for smaller fish that's at 5 grams, one that's about 20 grams, and one that's at 100 grams here. And so what you're seeing is that the growth rates of the larger fish relative to its own body size here is going to be less so than for the smallest one here. And now if we overlay the temperatures that Tahoe offers above the thermocline over the course of the summer, and we're going to include October in this because the lake's still pretty strongly stratified through October, it spans this range here, so roughly about 13 degrees or 12 degrees centigrade up to maybe 20-ish. Okay, so what it's telling us is that we're on the warm side of the curve, but there's plenty of scope for growth for certainly the smallest fish, the medium-sized fish, and even the larger ones. And as the the thermocline heats up, I'm sorry, the surface waters heat up, they may move into the thermocline to get access to some of those cooler waters to balance out the metabolic needs that they have at that point. So all this is doing is sort of setting some boundaries on what these fish might be capable of, but what we don't know yet is actually what are these feeding rates. What we're going to do is look at the kokanee and use them as a surrogate, because early in their life it looks like some of their diets are similar to what the historic cutthroat trout diets might have been. And we'll get to that in a minute here. The other key ingredient here is that lake trout tend to become very unhappy between 11 and 13 degrees centigrade, and so it's rare to find them above 13 degrees centigrade. And so you'll often, if we look at, here's a bunch of thermal profiles from a couple different years, and we can just overlay that zone where, so this is depth along this axis here, this is temperature, we're getting warmer as we go to the right. This shaded zone is the zone where the temperatures would be below that 11 degrees, and then the tail is sticking out to the 13 degree zone there. So by and large, we would expect, based on their thermal tolerance, for these lake trout to stay largely below this, say, 25 meter zone. And in fact, back in the 90s when we were doing gill netting all the way down the slope zone of the lake, what we found was the majority of the fish, except very few, were in that upper 0 to 25 meter layer. The majority across all seasons were predominantly in this 25 to 50 meter zone here, and they were dropping off as we got deeper, but by and large, I mean, the bulk of the population as well is below the thermocline there. Okay, so it's not that they won't make little forays up into that warmer water, but they will probably only do that when it's profitable to do so, and I'm actually going to show you an example of that in a bit. Okay, so one of the hypotheses that are probably essential when we think about reintroductions is there going to be a thermal niche that allows the cutthroat some segregation from their primary potential predators, especially during the critical period where maybe those juveniles can get a growth spurt and, number one, grow to outgrow a number of their predators, but also have a chance to disperse and acclimate to the lake as they enter the system. This, in fact, was found in the fall and leaf study by Alchokachi et al., but you can independently arrive at that just based on first principles as I was developing it here for you. The depth range is going to change a little bit between fall and leaf and Tahoe, again, because of the size of the lake, the bathymetry, the thermal profiles that we see. And so, again, in Tahoe, we're talking about this July through October period. The surface through potentially 25 meters, but at least that surface to 10 meter layer should be a good hard refuge for these fish while they're first growing in the lake here. Okay. Secondarily, the smaller cutthroat, because of that thermal tolerance, should benefit a bit more than the larger ones. So as they grow, their benefit is they're outgrowing some of their predators. As they grow, they may have to shift down to a little more exposure to potential predators, but those are trade-offs that become part of the hypothesis. What in fact is going to play out when this all occurs. And then what that means then is when we overlay this thermal regime with the bathymetric features of the lake, if there are shelf zones that are shallow enough, those could create some of these localized refuges that could be really critically important for cutthroat trout during key portions of the year. And if we look at Tahoe here, you can imagine now these lines are, they're just like a topographic map on that you see if you're going hiking, but in this case they're going deeper. The problem is it's a pretty crude scale. Each of these lines represents 100 meters or 300 feet deep. So these red shaded areas are just on a very crude sense highlighting some potential areas where you might expect some refuges to play out during those stratified periods. Now, as the lake cools down and destratifies in the late fall through spring months, there's not going to be any thermal refuge at that point, but the idea is that these fish have dispersed and actually everybody's metabolism is dialing back because the temperature is getting lower. Nobody's eating quite so much at that point, so that may be less of an issue when everybody's mixed up in the thermocline later in the year. Okay. Now I mentioned that lake trout are capable of moving up into the water column. I'd like to know the source of this, whether Bob or Brant or Scott or somebody took this photo. I've been trying to figure that out for about 20 years now. But what this shows actually, it actually is showing 2 points. This is actually a lake trout in about 10 meters or less of water during the summer, and there are a bunch of the native minnows. This is right along Rubicon here, where, okay, so these fish, it's during the summer, they're above the thermocline in warm water. But on a number of occasions when we've been diving, both when I was working here directly and then when my own students came later on in the 90s, there have been times where we're scuba diving in these very steep slope areas, and lake trout will come rocketing up past us into very shallow water. And then 5 or 10 minutes later, they go rocketing back down instead. Now, this photo, what it's capturing is these fish are actually up foraging on the minnows in very shallow water. Well, this is one of the few cases in a lake like Tahoe where this is a profitable venture. Why? Because they can take an elevator, they can go almost vertical up to that shallow area. And this whole zone here is very complex rocky habitat. That's the favorite habitat of all these minnows. You find, if you're going to find a swarm of minnows, they're usually in conjunction with this sort of habitat. So the water is very clear in Tahoe relative to virtually everywhere else. That was the other point I was going to make, though. Despite the fact that this is almost distilled water by lake water standards, it's still difficult to see that fish, isn't it? And it's even more difficult to see these guys here. So even though they have some of the better visual characteristics in a lake like Tahoe, they still have limited vision. And so when they go up into the water column, it's not like when you see a lot of the open water marine type videos where you can see fish from a long ways away. You're actually somewhat limited here, and the fish are absolutely limited. If you could see this, there's actually about a 1 meter halo around this fish, and it turns out when you do laboratory studies, that's the distance at which a lake trout will react to a smaller fish. Beyond that point, they don't even bother. And so when they come up into these zones here, they have quick access to an area where there's a high probability of running into prey, so it's a predictable area. They can go up, forage quickly before their body warms up, and then get back down. So you think about a slab of meat, for instance, not to get too crass, but it's going to take that a while for it to warm up, right? So you can take it from one temperature and bring it up to maybe 10 degrees warmer, and it's still going to take it a little while to warm up. So if these guys are operating, foraging up here for up to 10 minutes, that's really not long enough for that to change their temperature. Now, granted, their gills work more like a radiator in your car, so I was exaggerating there. Nonetheless, you can kind of get a feel for what I'm talking about, is that there is some thermal inertia these fish can enjoy when they come up, forage. If they find the fish, they can pick them off, move back down. If they don't find the fish, they zoom back down and maybe try later. So these sorts of areas are probably not going to be great cutthroat habitat initially. But in these zones here, now imagine a fish has to maybe travel a kilometer or so this direction to get up to those depths, to get from an area where it's deep enough and cold enough for them to stay long term. It's less likely, less profitable for them to do that. And so that's the reason why some of these shelf areas could potentially be a refuge. Okay, so this is part of this hypothesis about potential thermal refuges that they set up during some critical periods in their life. Okay, so that's kind of the environmental niche, and we've been toying a bit with some of the ecological interactions that relate to that. Let's talk a little more directly about that now. Okay, so historically, what did the cutthroat feed on? Are those foods still available? And whether they are or not, are there alternative foods that have also emerged in the interim due to all these introductions and extirpations that have occurred. Is the food supply sufficient to really generate the growth that these animals need? And is that food going to be available in the areas that are going to allow them access to it? And then we have to also be concerned about whether there are competitors that are also modifying the foodscape out there for these animals as well. And then in terms of predation, are there conditions that are going to either make predation a big issue, or is it going to, are there periods and places that predation can be really minimized? And what we want to do is look at how that all plays out. Okay, so let's get to the historic food web. This is a nice simplified version of it, where Lahont and cutthroat trout, especially the young ones, were feeding mostly on zooplankton. And then as they grew, they incorporate the minnows like tui chub and then also mountain whitefish into their diet. So what we're hypothesizing is that they will emulate that same diet composition to the extent possible when they come back into the lake here. What we don't know is what role the leaves will play in the system. Will they actually contribute to the diet of cutthroat trout, or are they going to be a competitor instead? That remains to be seen. We expect, again, as the cutthroat trout grow, that they'll eat the minnows, and they'll actually eat the kokanee as well. We know in other lake systems that cutthroat trout are significant predators on, say, juvenile sockeye salmon and also kokanee in a variety of systems. So that's actually a good thing that we've got a forage base, and that they have the ability to diversify their feeding portfolio, shall we say here. Okay, and then also, will kokanee and mysids compete for the zooplankton with these small cutthroat trout? So will there be a window where there's more competition, and then as the cutthroat grow, do they grow beyond that and increase the variety of foods that they can feed on and persist? Okay, and so as the large cutthroat grow and become more predatory, then they get into the same guild as, say, the brown trout and the lake trout, which feed, the large individuals anyway, feed pretty heavily on some fish. And so you've got multiple roles where a lake trout and brown trout may be predators, but also the large cutthroat can be predators, and they can eat each other. Okay, so a cutthroat can eat lake trout, they can eat brown trout, lake trout can eat everybody as well. So it can go round robin. It's all a matter of access and opportunity. Okay, so this is a more contemporary food web here. So now our apex predator is lake trout, and brown trout would be alongside that. The lake trout, and very importantly now, they're feeding very heavily on mysids currently. The planktivorous fish are kokanee, tui chub, Lahontan red sides, among other species. The benthic feeding fish, the ones that are feeding on the bottom, are Tahoe suckers and sculpin. Then we've got the zooplankton now. We've lost our Daphnia, but we do have copepods here. So we've got Diaptomus and Epicura that are both available. If we add cutthroat trout, then some of the hypothesized linkages are going to be that the smaller Lahontan cutthroat, which that line didn't come in, they'll be predominantly feeding on zooplankton, probably some insects, and the question mark is whether or not mysids will contribute at all to their diet or not. The larger Lahontan cutthroat trout will be feeding on a variety of fishes and potentially be cannibalistic as well. But they'll largely outgrow the size where they would be vulnerable to the lake trout. So we'll show you some of those dynamics here in a bit as well. Okay, you can't talk about Tahoe without talking a bit about the role of mysids here, because they really are one of the most influential species in a number of these western lakes after they were introduced. Okay, so for Tahoe, I'm going to take a very fish perspective on this because there's been lots and lots of other information that's come along. So prior to the mysid introduction, the kokanee were averaging, say, 15 to 20 inches long when they reached the size where they were going to spawn. And so that their average size is indicated by this red line here. After the mysid introduction, of course, we had the crash in the Daphnia population. And now we saw this decline in the size of the adult kokanee, such that it's down around, say, 10 to 13 inches. And actually, this time scale only goes to the mid-90s here, so I'm real curious to see what it is currently. Actually, this year, they were actually in the realm of about 12, 13 inches, the fish that we've been seeing. Actually, I see the guys that are making, you guys, what size have you been getting the kokanee at?
10 to 13.
Yeah.
Last year was better, though. We come up to 18, 17 inches.
Yeah, one of the things that goes on with the kokanee in particular is you notice when you have a lot of them available, their size goes down, so there's this density-dependent effect on their growth. So typically when they're bigger, it generally means there's fewer of them. If we're lucky, it meant it was actually a more productive year in general with more zooplankton production. But often, they're very, very responsive to their own density out there, especially in these lakes that are relatively unproductive. Okay, so even though we still have quite a lot of population fluctuation in terms of abundance, as indicated by these bars here, the overall size of these fish has declined, and so the overall biomass of kokanee in the lake has declined as a result of the Mysis population. Now, this is work that has never been published, but I just wanted to show you an example of relative effects of different species in the food web here. What we have on these two curves, the green and the blue, are the estimates of the biomass of adult copepods in the basin. So the blue line would be their biomass, the green line would be their biomass plus production. So the production is their growth and maybe reproduction that adds some additional adult copepod flesh into the lake during different months of the year. We've got a couple of years underway here. And then what we have are the consumption rates as estimated from energetics modeling. As I showed you before, these blue boxes here, that's how much the kokanee are eating. In other words, what it's saying is even though this is probably varying a lot, it doesn't vary enough to actually show in relation to the scale of this axis here. And so we're talking about metric tons of food out here. So in this case, this is 8,000 metric tons of copepod flesh, adult copepod flesh out in the lake there. And then what we have this is the metric tons of mysid consumption on food in order to grow those mysids. And so what this shows is if mysids were only eating copepods, that sometime during certain parts of the year, they could make a living on copepods, but other times of the year, there's not enough copepod biomass or production to support the mysids. And in fact, when we look at stable isotope analysis, it indicates that the mysids are actually feeding quite a bit on either phytoplankton or detritus instead. In fact, their signal is very similar to the zooplankton that they're eating. And so probably only a relatively small fraction of their diet is actually composed of copepods. In a way, that's good news in that it reduces their consumption demand on copepods overall and makes them a little less of a competitor. Okay? If we move to a different lake, this is Flathead Lake here, what we see are this is the energy budget of lake trout in Flathead Lake, and what we see are these reddish bars. That's the contribution of mysids to the energy balance of these fish over a broad size range. So from the very juvenile lake trout up to those that are, say, 25 inches long, the majority of their energy is coming from mysids. And it's only as these fish get bigger that all these other colors pop in. Those are the fish contributions to the diet there. So what we see are that mysids are a very important part of the energy budget, especially for younger lake trout. And it's not just in Flathead Lake. This is work from Gary Feedy, who is doing a master's degree with me early on in the 90s. This hatch component, that's all mysids. So again, we're seeing that most of the energy density over a range of sizes is composed of mysids. And then this is a similar graph from Lake Chelan in Washington, has a similar composition of prey there. Again, in this case, the yellow bars, that's the mysids. What I want to point out, though, is that In the shallow basin, by shallow I'm talking about, say, 60 to 100 meters deep, mysids compose a much larger fraction of the energy budget for lake trout in that system, whereas you get into the very deep basin, they contribute less. Okay? So when you have this bathymetry where the bottom is shallow enough where it's deep enough to support mysids because of their temperature regime, but it's too shallow for them to get down in dark, deep water where they can hide from the lake trout. The lake trout can really clean up on them on the bottom. They're in very high densities there, and it makes for very good food. Okay, so we can't talk about cutthroat in the west without talking about the potential for predation here. And so what we see is that the predation impacts between native trout and lake trout vary quite a bit among lakes. So there was an experimental reintroduction of Lahontan cutthroat trout up in Fallen Leaf Lake, and we've seen that that they're surviving there despite heavy predation by lake trout. In fact, they're seeing some spawners up in Glen Alpine Creek and maybe some other tributaries. So that's a fairly encouraging sign in that you're getting fish surviving several years to get to a spawning state, and enough of them that you can actually detect them, because there's a needle in the haystack when you think about looking through time and space to find the spawners. When we look at a variety of other lakes, they also coexist in Bear Lake, where you've got stocked lake trout there. However, we've got dramatic declines in both Yellowstone and Flathead lakes when we've got these expanding lake trout populations. We've had really precipitous declines in cutthroat trout populations, both in Yellowstone and in Flathead. And in Flathead, there are a number of other species. Kokanee in particular just completely went bottomed out in that system there. And then in Lake Chelan, which I also showed you earlier, we've got hatchery and wild westlope cuts that are providing a fishery in there. And again, we've got a large population of lake trout. So what's going on? I mean, you've got similar assemblages of fish, and yet we get these different results. Okay, so that's part of the hypotheses that we're trying to develop here through this program, is look at what are the mechanisms that will play out and affect the level of predation mortality, and is that going to be significant enough that it's actually regulating the population of cutthroat trout, or is it going to be a minimal effect there? Okay, I think I just said that. Okay, and as an example, this is Bear Lake. If we look at different snapshots of the food web in different seasons of the year, so spring, summer, fall, and winter, and I just want to highlight these red arrows these are juvenile Bear Lake cutthroat trout. And in the spring, when you don't have thermal stratification, you have pretty heavy predation by both the lake trout and the cutthroat trout, cannibalizing their own brethren there. In the summer, you do have thermal stratification. You have a little bit of cannibalization going on by the cutthroat trout, but the lake trout are largely laying off of them and staying down, feeding on deeper water prey. Okay, in the fall, not much going on. In the winter, again, things are dialed back, so yeah, they're feeding on them, but at a low rate, and there are alternatives. Part of the reason in Bear Lake, again, it's a tilt block lake rather than a graven lake here, where you had the whole floor of the lake just kind of dropped in Tahoe. In Bear Lake, it just kind of tilted on one side, and so you have these vast areas of relatively shallow zones that could provide refuge for the cutthroat trout in that zone, relative to the temperatures that need to be cold enough for the lake trout down in this area here. Okay, so to finish out the predation part, we just want to mention the critical relationship between growth and predation. So I said initially that big is better for these fish. Part of the reason for that, again, I'm going back to some other lakes as examples. This is a relationship of the size of lake trout that have eaten fish prey, and this is the size of the fish prey that we find in their gut. So we've got color-coded prey. These red ones are kokanee. These green ones are lake whitefish. And what we're seeing is that lake trout are capable of eating fish that are up to 50% of their own body length. Right? Okay, so they're capable of that. They can do it. They average about 30% of their body length. But you can use these relationships then to start going into a particular system and saying, if you know what the size structure of your predator population is, we can now play games like, if this is our prey length, as they grow along this axis here, we can start seeing how different relationships change. So for instance, as kokanee grew in Flathead Lake, the abundance of lake trout that were capable of feeding on them declined really rapidly. Okay. The biomass, or I should say, and then the numbers of kokanee that were consumed also declined really, really rapidly. Okay. What's happening, though, is as these fish are growing, their body mass also increases a lot, so it takes fewer kokanee to feed a lake trout. And so this is, although the lake trout are actually eating quite a bit of kokanee, that biomass of kokanee that they're eating is translating into fewer and fewer kokanee as well. And so you can play games with, in fact, what the agencies did was they introduced kokanee at this size, and then as the kokanee grew over a few months, they were able to reduce their mortality rate to about 5 or 10% of what it would have been initially. And so you can you can customize this sort of analysis to your particular basin and populations of fish, and then actually track them through. This is still Flathead Lake kokanee. What we saw was the size at which these fish were first stocked into the lake as yearlings at about 6 inches long or so. This was in May, and then July, August, and October, you can see them growing. It wasn't until October that they outgrew the majority of their predators. But if they're outgrowing those predators during the time when they're thermally segregated, then that works. If they're not thermally segregated, then you've got a bigger problem in terms of potential predation. Okay. Should have gone the other way. Okay, so we're trying to compile all this stuff and then put that in the context of what we're doing currently here. And so what we're really focused on is what's the distribution and abundance of different key elements of the food web in the pelagic or open water zone of Lake Tahoe. And so to get at the fish, and to some degree the Mysis, we're using hydroacoustics. That's essentially just sonar, but it's a scientific grade sonar that allows us to quantify fish by density in different layers of the water column and by size. So all these red lines you're seeing are transects that we're taking across the lake, and we're shooting down through the water column. We're also going to do midwater trawling, so those layers that have a little bit higher densities of these pelagic fishes, we're going to use those to target midwater trawling so we actually get our hands on these fish. This is the exciting part for us in that we've never had the capability. In fact, if we look at lakes around the West, it's actually quite hard to get usable numbers of fish with netting gear. And particularly it's challenging in a lake that has the low productivity that Lake Tahoe has. And so having fairly capable midwater trawl will give us the opportunity to get our hands on biological samples so we can actually see whether or not all these pelagic fish are in fact kokanee, or they could actually be some of these native minnows that are pelagic. Historically they were pelagic, but how far offshore did they actually go? Were they just kind of creating this halo around the lake, or do they actually make use of the whole open water arena? We haven't really had the capability of knowing that until doing this midwater trawling, so that's another reason for some excitement there. Zooplankton sampling, we're just specializing in a couple areas for now, but we're doing a depth stratified sampling, so we're looking at the density in the upper 10 meters, so that's above the thermocline, then within the thermocline, and then a swath through the below the thermocline, so we get an idea of how the densities of zooplankton play out, so we know what the trade-offs are for these fish. If they select a habitat based on the thermal regime, what's the food payoff to them in those zones? And we're doing some repeated transects across different areas that have different bottom depths so we can see if there's some pattern there. Again, at a pilot level right now to try and sort out what's going on. We hope to be able to tap into the long-term data set from the offshore sampling as well to see and use that in conjunction with these data to play back and forth between what's the time series look like versus some of this more tactical level sampling that's going on currently. And then we're doing vertical mysid hauls through the water column at all these spots that have these black squares here. So we're using a 1 meter Mysis net in diameter. Here it is. It has a 1 millimeter opening mesh size to it, and we'll be towing that up through from about 100 meters to the surface. From our acoustic work, it looks like at night that scattering layer of Mysis comes up primarily to 60 meters, and Peters. So if we go down to about 100 meters deep, we're actually capturing the lower end of that pretty well. And so we can look at what's the density of Mysis in, say, this area of lake bottom. Essentially, we're kind of scooping everything up that would have been on a lake bottom there, and we can talk about Mysis in terms of their density per square meter or hectare in the lake, as well as on a volumetric basis later on. So this is a schematic of what hydroacoustics looks like. You're sending sound down through the water. You can actually quantify the density of fish by size in different layers of the water column. You can get an output like this that also gives you a pictorial of what's in the water column. This is not Lake Tahoe, by the way. If you do it during the day periods, you can get a sense for what the distribution patterns look like then. Oftentimes you have fish that are schooling. Those schools are very elusive. It's hard to actually detect them without a huge amount of effort. But you can see where the different sizes of fish are playing out, and even potentially see what the Mysis layer looks like at that point. At night, you can see if this Mysis layer comes up. Typically, the schools split apart at that point, and that's why we do midwater trawling at night, is because as the fish split apart, it's very hard to find a school. It's a needle in a haystack. But as the fish spread out, now they're more uniformly distributed. I use that term very, very loosely. But it gives you a much greater opportunity to pick them up in a net, and it also makes it easier and more accurate to assess them using hydroacoustic gear. And so we can take a midwater trawl through specific depth intervals in the water column and identify what species are actually there, what's the size distribution of them, and then the big benefit is that we're actually getting our hands on biological samples, so we can do things like back calculate what their growth is, what's their diet, what's their size, do stable isotopes on them, a whole variety of things that feed back into a lot of these other analyses. Okay, so here's just a quick cartoon of daytime distributions, pretty low densities out there. This is at dusk, so you're seeing more densities of fish up in this zone here circled. You can see the Mysis layer starting to come up through the water column here. And then at night, you actually see more of these fish targets in this layer centered around about 20 meters. And the Mysis layer is topping out at between, well, about 50 meters or so. Some are encroaching a little bit higher. We can use that interchangeably with the net sampling to do a better job of quantifying what's going on in time and space, and having the context for how they're using the environment, where they're located, and what they're doing at the time. Okay, so this is just a more quantitative version where during daylight, what we're seeing here is depth along this axis. This is the density of fish per 1,000 cubic meters. So this room is maybe half of that volume here. If we stacked, well, maybe a third. If we had 3 of these rooms stacked into a cube, that would be about 1,000 cubic meters. And so we're seeing a fraction of a fish per 1,000 cubic meters here, according to these densities here. Okay, but during daylight, very, very few single fish available. They're probably in schools at this same depth interval. At night or at dusk, we see the schools disperse and then fully disperse at night, but they're remaining relatively in that same depth interval there. Okay, so that's important. Number one, we can quantify this and actually get abundance estimates on the number of these pelagic fish out there. From the net sampling, we can partition those into different species and size groups. We can also do the size groups from the acoustics itself. And we can also look at how they're distributed through different parts of the lake. So this is if we look at the open water, or I'm sorry, here's the open water transects we had going across the north, central, and south region. We're seeing that the densities are somewhat similar, with a little bit higher density of these pelagic fish in the southern most area, but it's rewarding to see that you actually have measurable densities across all three thirds of the lake, if you will. And so that's in the open water area. If we go up and down the slopes over similar depth range, though, we also see that there's reasonably similar densities of fish in those zones as well. So it's telling us that this deep water community or midwater community is utilizing a lot of these habitats out there, and that we can start focusing in on what they're doing. Okay, we can use that information again. We know what the depth of those fish are. We can overlay that with these thermal patterns through time, and then plot out what the thermal experience of a kokanee would be over the course of the year. Okay, so they're getting up to maybe 16 degrees in September, down to 6 degrees in the wintertime. We can use that as an input into this energetics model I showed you earlier. We can run that model to estimate consumption, but now we can do this for individual, representative individuals from each age or size class of our consumer, and then get a consumption estimate of those individuals through time. Now, also recognize that we typically have a lot more of the younger fish than the older fish, so the smaller ones are going to be more abundant than the older ones here. So we can incorporate the size, structure, and abundance into those consumption estimates to come up with a population level consumption estimate. So how much food is this kokanee population eating on a monthly basis, seasonal basis, or across the year? And then if we know something about the prey that they're feeding on in terms of their biomass, then we can actually convert that consumption estimate into a mortality, or what fraction of the overall pie of prey is being consumed by each one of these consumers out there. So I showed you an example based on kokanee, but we can do that for these other species, provided that we sample them in a similar manner. Okay, and I'm just about done, so hang with me for just a second here. So if we look at the consumption of these fish, I'm just doing a simulation, so let's assume we have 1 million kokanee fry enter the lake from Taylor Creek when they start life. As they start here, and now we're just going to march through the seasons of each year of their life here, their abundance is going to go down precipitously. You know, it's a hard life for a fish. They start with 1 million, you end up with maybe 80,000 of them or so at the end of their life. But their abundance is going down through time. Their body weight is going up. So we have to factor both of those things in through the life of those fish in order to look at those population level consumption estimates. And these are those consumption estimates based on each age class of kokanee, different seasons of the year. Now this is ginned up data just based on the diet information we got from these fish last month. But what we're seeing is they're feeding on mysids, which was interesting. We were expecting them to feed almost exclusively on the copepods, so that would be the epicure and the diaphanous, but they're also feeding to a considerable degree on mysis. At least the adults are. Okay, so this can give us an estimate of what biomass every cohort of 1 million new kokanee are eating over the course of their life out there. The other really important output of that simulation is that we get a feeding rate in terms of their percent of their maximum. And for the young age 0 fish, they're eating at about 34% of their maximum rate on average over the whole year, but 45 to 55% as we get to these older age classes here. So if you think back to that original graph, and I'm going to show it to you here again, we assume 50% maximum consumption. So in fact, these curves are not too far off in terms of the growth potential that these fish should be able to enjoy if they're staying above the thermocline. And again, like I said, as the fish grow, maybe they have to encroach into the thermocline to stay in a reasonable temperature regime. But it appears that there's sufficient food based on, again, kokanee is a surrogate. So that's the hypothesis, is whether or not these cutthroat are going to behave like the kokanee. Okay, so we're virtually done. I'm just going to call these preliminary findings and not really conclusions because we're just underway now. It does appear that there's a thermal regime that allows for a refuge for these fish, the Lahontan cutthroat, during the stratified period of the year. This could be an effective deterrent against predation, particularly for the younger age classes. and there does appear to be sufficient food for kokanee. Again, the juveniles will probably benefit from this the most. Mysids are a very important energy source for both juvenile and adult lake trout, but will they be either a net competitor or a food source for the cutthroat trout and kokanee? That remains to be seen. And then I'm just going to finish with this overall platitude that if we can quantify these interactions through time and space and pay attention to the different life stages and do it in as mechanistic a way as we possibly can, it really helps us identify some potential bottlenecks that may inhibit production at various life stages or enhance or look at where there's some opportunities for growth to exist. And this will then feed kind of in an iterative manner the research and management options in terms of as we adapt going through different steps. What do we learn? How can we implement that into the next stage of this grand experiment here? So thanks for being patient with me. I'll take questions. Thanks.
A significant difference between the cutthroat and the kokanee that you're using as kind of a model is the spawning period for kokanee is in October, whereas the cutthroat is in spring, early spring.
Yes.
So if you're using a thermal refuge, doesn't that throw it off by half a year? And when the fish fry or juveniles move into the lake, then will that affect their predation then?
What we're focusing on entirely right now is their lake life. So for that, so it's entirely relevant for that portion of it. You're right. The entry times are going to be quite a bit different, probably off by about 6 months in terms of when kokanee come in and when cutthroat trout come in. But cutthroat can also exhibit a variety of life stages where you may have some that pulse out almost immediately after they hatch. You've got other life history strategies where they may stay for several years before coming downstream and utilizing the lake. We're not even focused on the stream side of the equation right now. We're trying to answer the question of what sort of a niche, what does the niche look like in the lake environment currently?
Does any of this give you any insight as to what happened around 1940 that took the LCT out of the lake? Do you believe that was a lake impact, or is that more probably stream?
I think that it's still, the original idea is still hold. This doesn't dispute that at all. And probably because a lot of the major players that are currently in the lake didn't even exist during the period when the Lahontan cutthroat were reigning supreme. We also don't know really what the trend in, say, the lake trout population was over that whole era there. What we've seen is the lake trout typically take off after mysis have come in, but Lake Tahoe has its own interesting nuances in terms of things that may be limiting the reproduction of lake trout too. It seems like there's a lot of lake predators out here. Part of the work I did in the early 90s was looking at what might be limiting, why we didn't see a lot more evidence of spawning in some of these slope zone habitats that looked like it should be great spawning habitat for a lake trout, and yet we saw very little of it. We would see aggregations of fish there, but little to no evidence of spawning. In fact, where we did find positive spawning were in these seamounts that were down in the south end of the lake that were coming up out of really deep water, but the tops of them were around 40 to 50 meters deep. We had weeds on top, charophytes, that were actually providing the structure to hold the eggs there. And the only predators that were out there were bigger lake trout. So what could have been limiting lake trout all along is not so much a food source as just a habitat that suppressed the egg predators from them. Whereas in a lot of these other lake systems, particularly Flathead, you had this. I go back to that one a lot because it's probably the most spectacular example. Mysis came in about 1980, and by 1985, they established a really strong population. What also was going on at that time, though, was that
The kokanee population was producing about 500,000 to 1 million adults. That was both in terms, so the harvest was about 200,000 good-sized kokanee, and then another half of those were going up and spawning about 80 miles upstream, just below McDonald Lake in Glacier National Park. When the Mysis established, in the course, so early 80s, you see no evidence of any problem, and then 1985, all of a sudden you go from hundreds of thousands of large kokanee to just a couple thousand, just as fast as that. A year and a half, they were gone. And the hypothesis is that as the Mysis came in, they were essentially relieved a lot of the mortality pressure on younger lake trout. Turns out that cannibalism suppresses lake trout populations in a lot of places, and there are a lot of elements to the story. I can't get into everything, but there was a lot of evidence of cannibalism in Flathead Lake. If you can imagine Mysis coming into a system, the lake trout, historically, the young ones typically are at radically different depths than the adults in most of their native range, probably to avoid that very issue. They don't always have that ability in a lake that they've been introduced into. So what may have been happening is they could either seek refuge in, say, rubble piles or what have you, or they have to go out and feed. So if they stayed in the rubble pile, they're going to deplete whatever food is there in pretty short order, and eventually they're going to have to go out and feed around other parts of the lake. When they do that, it makes them vulnerable to predation by these larger lake trout. Now think about what Mysis do. When they come in, they do this diel vertical migration where they carpet out on the bottom during daylight, and they go up into the water column at night. So they carpet out during daylight, this thick layer of lots of meaty mysids that they can just vacuum up off the bottom during daylight. Even if they deplete that resource locally in that patch of rocks, it doesn't matter because those mysids go up, they come back down, they recarpet that same zone. And so even an incremental increase in survival that was imposed by that, that's our hypothesis about what happened. What in reality, what we can say is that over those intervening 10 years, the lake trout population went from a very small fraction of the overall lake community to it increased by 20-fold. And at the same time, you had a reciprocal decline in, well, you had a complete crash in kokanee. You had a radical decline in the West Slope cutthroat trout, bull trout, and pygmy whitefish, some of the other native species that were there. But this was in response to an absolute explosion in the lake trout population that was mitigated by a new introduction of yet another non-native food source there. So for the longest time, the argument was that mysids were just out competing kokanee for the zooplankton, and so they weren't growing as well. But if you actually piece it out, yeah, the kokanee would have grown less, but you wouldn't have had this massive mortality instead. So I'm kind of just tickling the edges of what may have occurred here in Tahoe, but I don't think that the food web was directly responsible for their extirpation originally. I think there's been other pieces of the puzzle. Certainly, the deforestation of the basin, the decline in the quality of the tributaries as a result of that, the really strong overharvest of those large Lahontan cutthroat trout historically as well. That's the conventional wisdom currently, is that that led to the demise of the cutthroat in this lake here. And so far, we find nothing to refute that. Yeah, John.
Any results from the stocking and falling lake for LCTs that gives any indication on this shelf and this immediate thermal refuge?
Well, it seems like the same things are happening. Now, Al-Shokachi paper was indicating that there was a depth at which the lake trout generally stayed below that. The cutthroat tended to stay above that. But again, it only lasts during that thermally stratified period. Okay, Fall Leaf Lake's a much smaller lake, so a lot of the scale of the issue is a big question here. And I'm not aware of how much follow-up evaluation has been going on in order to really do that. It's very hard to track
fish through their entire life stage. That's why I say it's impressive to actually see evidence of spawners, because a lot has to go right for fish to survive that long. As I showed you, just natural survival rates are such for a fish that you don't get very many that survive from the initial number. They both survived and they found appropriate spawning habitat there. But in terms of the actual numbers, other people probably know more than I do currently about what the status is there. Hey, Charles.
At some point, you'll probably have to include in your model the fact that the surface waters are warming so much more rapidly than the whole water column. And this will thin the epilimnion and provide maybe too hot a refuge.
Yeah, it both changes the volume and creates a warmer refuge there. That's right. In other systems, this is an interesting counterintuitive result of that is, again, using kokanee and lake trout, mysids, and zooplankton. Some reservoirs in Colorado where they saw these years where there was less snowfall, so the reservoirs in general were lower. It was hotter overall, so you had a very strong but thin thermocline set up. That was actually advantageous to the kokanee and the daphnia because it segregated them from the mysids and lake trout. And so the kokanee could happily feed away at the daphnia. The daphnia were at a temperature where they could reproduce really quickly, and they were in that upper photic zone. The lake trout had to settle for mysids as their only food during that time. Okay, so that'll work for a while. If climate trends even further, then of course we get into an area where it becomes much warmer, and we have to reevaluate how that whole thermal regime plays out for sure.
One interesting difference between Fallen Leaf Lake and Tahoe is that at Tahoe, because of the greater width, we get these significant thermal upwellings, particularly in the spring and the summer. And those areas you were showing as potential thermal refugia would actually, once a week get this cold water coming up, almost an elevator. So it may be interesting to see if there are differences between the west shore and the east shore, where the upwellings don't seem to ever occur.
Yeah, and then north-south too. So those areas that have the more gradual slope as opposed to a shelf with a fairly steep drop-off, or that sorts of topography can have a lot of influence. Certainly we see that when we look at, I do similar work out in the ocean, and so for instance the Gulf of Alaska, you see that the bathymetry there really has an impact on generating production of the phytoplankton and zooplankton, and it will create some hot spots for fish, but there's a disconnect at that level because there are 3 or 4 different things that can happen that are all equally plausible, and they all go in opposite directions. Hey, John.
Just another question. So when you're using kokanee as a surrogate, is that good for the whole life history of the kokanee?
No, we're really only using them as a way to kind of calibrate what would can we expect a planktivorous fish to feed at a reasonably high rate or a low rate there. And that's really all we're trying to do with the kokanee. We've got models generated that capture the physiology of cutthroat trout explicitly, but what we don't have are cutthroat trout in Lake Tahoe right now that we can track and check their performance. So absent that, right now we're just looking at what is another planktivore that historically looked like they, at least the juvenile cutthroat trout, were filling a similar niche to what the kokanee currently are. Let's take a look at how kokanee are feeding and sort out whether or not that's gets us in the ballpark there.
I have a question, not for Dave, but actually for some of the people who remove fish from lakes for a living. I mean, Dave has been touching on some of the history and the trends that the data has shown. I mean, did you hear anything that maybe differs from your own experiences like that?
So my experience is that the fish travel around the lake all the time, and not the same area.
But seasons, but overall trends of increasing and decreasing fish and the like, is that?
I think there's more suspended fish the last couple of years.
And I found that different this year, where we used to fish for the kokanee and catch a lot of lake trout underneath them. Like some years, 5-7 years ago, I mean, we catch a dozen lake trout underneath the kokanee. This year, we caught some nice lake trout underneath them, but nowhere near the numbers.
How were the kokanee catches this year
We
versus
caught
that?
in our fleet probably 70,000 kokanee this year.
And the year that you saw lots of lake trout hanging underneath them?
Still very good.
Was that the same or better even?
Yeah, oh, yeah.
Yeah, we'd like to be able to string those observations together and look at, can we start predicting when lake trout shift to foraging mode, or at least when enough so we can detect it, so that they're feeding more pelagically or not. And in order to do that, you would expect that there'd be a lot more food available, so it's a more predictable source for them to actually venture out offshore and go for them. Because the default really is, if they can't find those pelagic fish very, very well, then they're going to fill up partially on mysids and then do this kind of slope crawl to get at those things like crayfish and the minnows and the fish that are closer to the slope zone there. Yeah, well, thanks everybody.
How long, one last one, how long did your study go on?
Well, this is get our feet wet here to try and get reacclimated to the lake itself and try and plug some of the data gaps that we knew existed from long term. We were actually needing to have meetings to plan what's going to happen in the future here. So presumably multi-year, but all we're trying to do is set the context for how we plan future research and hopefully tie in with a lot of folks in this room as well.
Okay, so if there are no further questions, I'd like to thank Dave and thank you all for coming today.